Stream should be online. Give me a second to make sure that we are actually all good to go. Alright, it's kicking on. Turn up the volume and make sure audio is working. Alright, and it looks like we're ready to begin. I'll waste no time, and this time I'm not going to start with a 10-minute interjection about a single problem from the previous problem set. Ah, gosh, these problems. Anyways. Chapter 18, Integral Domains. One of the most important rings we study is the ring of integers. It was our first example of an algebraic structure. The first polynomial ring that we examined was z adjoined x. We also know that the integers sit naturally inside the field of rational numbers, Q. The ring of integers is the model for all integral domains. In this chapter, we will examine integral domains in general, answering questions about the ideal structure of integral domains, polynomial rings over integral domains, and whether or not an integral domain can be embedded into a field. Section 18.1, Field of Fractions. Every field is also an integral domain. However, there are many integral domains that are not fields. For example, the integers z form an integral domain, but not a field. A question that naturally arises is how we might associate an integral domain with a field. There is a natural way to construct the rationals q from the integers. The rationals can be represented as formal quotients of two integers. The rational numbers are certainly a field. In fact, it can be shown that the rationals are the smallest field that contain the integers. Given an integral domain D, our question now becomes how to construct the smallest field f containing D. We will do this in the way we constructed the rationals from the integers. An element p over q in Q is the quotient of two integers p and q. However, different pairs of integers can represent the same rational number. For instance, 1/2 equals 2/4 equals 3/6. We know that a over b is equal to c over d if and only if a times d is equal to b times c. A more formal way of considering this problem is to examine fractions in terms of equivalence relations. We can think of elements in Q as ordered pairs in z times z. A quotient p over q can then be written as pq. For instance, 3 over 7 would represent the fraction 3 over 7. So I'm going to quick write this. So we represent, given a field, we should probably do R. So if we have A, B in R times R, we'll commonly define this and write it as A over B. So because we have two pieces of information, we can express this as a coordinate, even if it's not the standard way we write it. So, we can think of elements in Q as ordered pairs in z times z. A quotient p over q can be written as pq. For instance, 3/7 would represent the fraction 3/7. However, there are problems if we consider all possible pairs in z times z. There is no fraction 5 over 0 corresponding to the pair 5, 0. Also, the pairs 3, 6, and 2, 4 both represent the fraction 1/2. The first problem is easily solved if we require the second coordinate to be non-zero. The second problem is solved by considering two pairs A, B, and CD to be equal if AD is equal to BC. If we use this approach of ordered pairs instead of fractions, then we can study integral domains in general. Let D be any integral domain, and let S be the set of AB in A, B, and D, and B is not equal to 0. Define a relation on A, B similar to CD if AD is equal to BC. So we'll write this. So we'll write S is equal to D times D star, where D star is equal to D minus, I should write D minus 0. And we define A, B is similar to CD if and only if AD is equal to BC. Lemma 18.1. The relation between elements of S is an equivalence relation. Proof. Since D is commutative, AB is equal to BA. Hence, the relation is reflexive on D. Now, suppose that AB is similar to CD. Then AD is equal to BC, or CB is equal to DA. Therefore, CD is similar to AB, and the relation is symmetric. Finally, to show that the relation is transitive, let AB be similar to CD, and CD be similar to EF. In this case, AD is equal to BC, and CF is equal to DE. Multiplying both sides of AD equals BE by F yields AFD is equal to ADF, is equal to BC of F, is equals to BD of E is equal to BED. Since D is an integral domain, we can deduce that AF is equal to BE, or AB is similar to EF. And this is by the previous cancellation law. So, from here, we will denote the set of equivalence classes on S by FD. So, FD is equal to, you could write this as S over the equivalence relation, if you're used to that theoretic terminology. So we will denote the set of equivalence classes on S by FD. We now need to define the operations of addition and multiplication on FD. Recall how fractions are added and multiplied in Q, that A over B plus C over D is equal to AD plus BC over BD, and A over B times C over D is equal to AC over BD. It seems reasonable to define the operations of addition and multiplication on F in a similar manner. If we define the equivalence class of A, B, and S by AB, then we are led to define the operations of addition and multiplication on FD by the equivalence class of AB plus the equivalence class of CD is equal to the equivalence class of AD plus BC, BD, and the equivalence class of AB times the equivalence class of CD is equal to the equivalence class of AC, BD, respectively. The next lemma demonstrates that these operations are independent of the choice of representatives from each equivalence class. So, lemma 18.2. The operations of addition and multiplication on FD are well defined. Proof. We will prove that the operation of addition is well defined. The proof that multiplication is well defined is left as an exercise. Let A1, B1 be equal to A2, B2, and C1, D1 be equal to C2, D2. We must show that A1, D1 plus B1, C1, B1 via D1 is equal to A2, D2 plus B2, C2, B2, D2. Or, equivalently, that A1, D1 plus B1, C1, B2, D2 is equal to B1, D1, A2, D2 plus B2, C2. Since A1 is equivalent to A2, A1, B1 is equivalent to A2, B2, and C1, D1 is equivalent to C2, D2, we know that A1, B2 is equal to B1, A2, and C1, D2 is equal to D1, C2. Therefore, A1, D1 plus B1, C1 times B2, D2 is equal to, oh gosh, we have a whole jumbled mess. We first expand it, then we use the commutativity of our operation. Then from that commutativity, we're able to swap out the respective operations using the identities held up here. And then we refactorize it. Lemma 18.3. The set of equivalence classes of S, FD, under the equivalence relation sim, together with the operations of addition and multiplication, defined by AB plus CD is equal to AD plus BC, BD, and AB times CD equals AC plus BD, is a field. Proof. The additive and multiplicative identities are 0, 1, and 1, 1 respectively. To show that 0, 1 is the additive identity, observe that AB plus 0, 1 equals A1 plus B0, B1 equals AB. It is easy to then show that 1, 1 is the multiplicative identity. Let A be an FD such that A is not equal to 0. Then BA is also an FD, and AB times BA is equal to 1, 1. Hence, BA is the multiplicative inverse for AB. Similarly, negative AB is the additive inverse of AB. We leave as an exercise the verification of the associative and commutative properties of multiplication in FD. We also leave it to the reader to show that FD is an abelian group under addition. It remains to show that the distributive property holds in FD. However, AB times EF plus CD times EF is equal to AE BF plus CE DF equals AE. This is a long string of equalities here, and then we're able to factor it out to the other side, and the lemma is proved. From here, the field FD in lemma 18.3 is called the field of fractions or the field of quotients of the integral domain D. Theorem 18.4. Let D be an integral domain, then D can be embedded in a field of fractions FD, where any element in FD can be expressed as the quotient of two elements in D. Furthermore, the field of fractions FD is unique in the sense that if E is any field containing D, then there is a map psi from FD to E giving an isomorphism with a subfield of E such that psi of A is equal to A for all elements A and D, where I identify an element A with its image in FD. So what this is basically saying is that suppose we have D. D has an inclusion map into E and an inclusion map into the field of fractions FD. And we're basically saying that there exists a unique morphism or a unique isomorphism onto a certain image. So I'll actually just write something here. Image of D as a subset of E. So there's basically a isomorphism, a unique isomorphism nonetheless, to any field that has, so we'll call this I1, I2, into that. And I2, we define I2 to be as follows. So I2 of D is equal to D1. Alright, so we have that. Alright, proof. We will first demonstrate that D can be embedded into the field FD. Define a map phi from D to FD by phi of A is equal to A1. Then for A and B in D, phi of A plus B equals A plus B1 equals A1 plus B1 equals phi of A plus phi of B, and phi of AB is equal to AB1 is equal to A1 B1 is equal to phi of A phi of B. Hence, phi is a homomorphism. To show that phi is 1-to-1, suppose that phi of A is equal to phi of B. Then A1 equals B1, or A equals A1 equals 1B equals B. Finally, any element of FD can be expressed as the quotient of two elements in D, since phi of A, phi of B to the negative 1, is equal to A1 B 1 to the negative 1 equals A1 1B equals AB. Now, let E be a field containing D, and define a map psi from FD to E by psi of AB is equal to AB minus 1. To show that psi is well defined, let A1 B1 be equal to A2 B2. Also, I should quick mention before I continue, we're able to make this definition by we were mentioning this canonical identification. So we identify the field D with an E, kind of like how the integers aren't actually in the rationals, right? The rationals are like pairs of integers, but we can still identify the integers within the rationals. That's what we're doing here. And that allows us to actually talk about this inverse without referring to like the element as being in the image of the inclusion into E. We're able to just refer to the image the element itself. To show that psi is well defined, let A1 B1 be equal to A2 B2. Then A1 B2 is equal to B1 A2, and therefore A1 B1 minus 1 equals A2 B2 minus 1, and C of A1 B1 is equal to C of A2 B2. If A, B, and C, D are in FD, then psi of AB plus CD equals psi of AD plus BC, BD is equal to AD plus BC, BD to the minus 1, equals AB to the minus 1 plus CD to the minus 1 is equal to psi of AB plus psi of CD. And psi of AB times CD is equal to psi of AC BD is equal to AC BD minus 1 is equal to AB minus 1 CD minus 1 is equal to psi of AB psi of CD. Therefore, psi is a homomorphism. To complete the proof of the theorem, we need to show that psi is 1-to-1. Suppose that psi of AB is equal to AB minus 1 is equal to 0. Then A is equal to 0B is equal to 0, and AB is equal to 0B. Therefore, the kernel of psi is a zero element 0B in FD, and psi is injective. Example 18.5. Since Q is a field, Qx is an integral domain. The field of fractions Qx is a set of all rational expressions P of x over Q of x, where P of x and Q of x are polynomials over the rationals, and Q of x is not the zero polynomial. We will denote this field by Q of x. So since we're going past that point and more so into the polynomial, so f of x is equal to f of x. Actually, let me use some more unintuitive notation. So if R is a field, we don't necessarily need a field, but it's just, yeah, it's nice to work with that. Then we have R of x is equal to, or if R is an integral domain, is equal to f of r to the x. So like the formal rational expressions of polynomials. This gets us rational functions. Example 18.5, yeah, okay, wait, we went over that, my bad. We'll leave the proofs of the following corollaries of theorem 18.4 as exercises. So, corollary 18.6. Let F be a field of characteristics 0. Then F contains a subfield isomorphic to Q. And corollary 18.7. Let F be a field of characteristic P. Then F contains a subfield isomorphic to Z sub P. These are very important, and they basically ensure you have some amount of structure on your fields, and that your fields will contain certain things that must be similar to something else. Anyways. 18.2. Factorization in integral domains. The building blocks of the integers are prime numbers. If F is a field, then irreducible polynomials in f of x play a role that is very similar to that of the prime numbers in the ring of integers. Given an arbitrary integral domain, we are led to the following series of definitions. First, let R be a commutative ring with identity, and let A and B be elements in R. We say that A divides B, and write A divides B, or A bar B, if there exists an element C in R, such that B is equal to AC. A unit in R is an element that has a multiplicative inverse. Two elements A and B are in R are said to be associates if there exists a unit U in R, such that A equals UB. Now, let D be an integral domain. A non-zero element P in D, such that it is not a unit, is said to be irreducible, provided that whenever P equals AB, either A or B is a unit. Furthermore, P is prime if P divides AB, if whenever P divides AB, either P divides A or P divides B. Example 18.8. It is important to notice that prime and irreducible elements do not always coincide. Let R be the subring with identity of Q adjoined xy, generated by x squared, y squared, and xy. Each of these elements is irreducible in R. However, xy is not prime, since xy divides x squared y squared, but does not divide either x squared or y squared. The fundamental theorem of arithmetic then states that every positive integer n greater than 1 can be factored into a product of prime numbers p1 all the way to pk, where the pi's are not necessarily distinct. We also know that such factorizations are unique up to the order of the pi's. We can easily extend this result to the integers. The question arises of whether or not such factorizations are possible in other rings. Generalizing this definition, we say an integral domain D is a unique factorization domain, or UFD, if D satisfies the following two criterion. First, let A and D, such that A is not equal to 0, and A is not a unit. Then A can be written as the product of irreducible elements in D. Second, let A be equal to P1 all the way to PR, equals Q1 all the way to QS, where the PI's and the QI's are irreducible. Then R is equal to S, and there is a permutation such that PI and Q pi j are associates for j equals 1 to R. So first of all, this is telling us that we have a factorization. This is telling us that our factorization is unique up to possibly, for the integer example, plus minus 1s, and just reordering. So example 18.9. The integers are a unique factorization domain by the fundamental theorem of arithmetic. Example 18.10. Not every integral domain is a unique factorization domain. The subring z adjoint square root of 3i is equal to a plus b square root of 3i of the complex numbers is an integral domain. Let z be equal to a plus b cubed root 3i, and define v from z square root of 3 to the natural numbers including 0 by noi of z, or nu of z, is equal to the absolute value of z squared, is equal to a squared plus 3b squared. It is clear that nu of z is greater than or equal to 0, with equality when z is equal to 0. Also, from our knowledge of complex numbers, we know that nu of zw is equal to nu of z nu of w. It is easy to show that if nu of z is equal to 1, then z is a unit, and that the only units of z squared root of 3i are 1 and minus 1. We claim that 4 has two different factorizations in the irreducible elements. 4 is equal to 2 times 2 is equal to 1 minus square root of 3i, 1 plus square root of 3i. We must show that each of these factors is an irreducible element in z square root of 3i. If 2 is not irreducible, then 2 is equal to zw for elements z, w, and z adjoined square root of 3i, where nu of z equals nu of w is equal to 2. However, there does not exist an element n in z adjoined square root of 3i, such that nu of z is equal to 2, because the equation a squared plus 3b squared equals 2 has no integer solutions. Therefore, 2 must be irreducible. A similar argument shows that both 1 minus square root of 3i and 1 plus square root of 3i are irreducible. Since 2 is not a unit multiple of either 1 minus square root of 3i or 1 plus square root of 3i, 4 has at least 2 different factorizations into irreducible elements. So basically, we show the factorization exists, we just show that it's not unique, in the sense that you can't just like reassociate, we just can't have things back up to reassociates. Principal ideal domains. Let R be a commutative ring with identity. Recall that a principal ideal generated by A and R is an ideal of the form A is equal to RA for all R and R. An integral domain in which every ideal is principal is called a principal ideal domain, or PID. So lemma 18.1. Let D be an integral domain, and let A be in D. Then A divides B if and only if the principal ideal generated by B is a subset of the principal ideal generated by A. A and B are associates if and only if the ideal generated by B is equal to the ideal generated by A. And A is a unit in D if and only if the principal ideal generated by A is the entire integral domain. So, 1. So first we're going to be starting off with this, I'll just highlight it. Suppose that A divides B, then B equals AX for some X in G. Hence, for every R in B and D, BR is equal to AXR is equal to AXR, and the ideal generated by B is a subset of the ideal generated by A. Conversely, suppose that B is a subset of A, then B is in A. Consequently, B equals AX for some X in D, and thus A divides B. 2. Changing where I'm highlighting. Since A and B are associates, there exists a unit U such that A is equal to UB. Therefore, B divides A, and the principal ideal generated by A is a subset of the principal ideal generated by B. Similarly, because of the fact that the unit has a multiplicative inverse, the principal ideal generated by B is a subset of the principal ideal generated by A. And as such, it follows that since they're both subsets of each other, they're the same. Conversely, suppose that the principal ideal generated by A is equal to the principal ideal generated by B. By part 1, A divides B and B divides A. Then A equals B of X and B equals A of Y for some X, Y, and D. Therefore, A is equal to B of X is equal to AY of X. Since D is an integral domain, XY is equal to 1. That is, X and Y are units and A and B are associates. 3. An element, I should again highlight. An element A and D is a unit if and only if A is an associate of 1. However, A is an associate of 1 if and only if the principal ideal generated by A is equal to the principal ideal generated by 1, which is equal to the entire integral domain D. So, let D be a PID. Oh, why is it scrolling like that? Let D be a PID, and the ideal generated by P be a non-zero ideal in D. Then I'll just call it Langle P is a maximal ideal if and only if P is irreducible. So proof. Suppose that the I'm gonna keep messing this up. The ideal generated by P is a maximal ideal. If some element A and D divides P, then the integral of the ideal generated by P is a subset of the ideal generated by A. Since the ideal generated by P is maximal, either D is equal to the ideal generated by A, or the ideal generated by P is equal to the ideal generated by A. Consequently, either A and P are associates, or A is a unit. Therefore, P is irreducible. Conversely, let P be irreducible. If the integral domain if the principal ideal generated by A is an ideal in D, such that the principal ideal generated by P is a subset of the principal ideal generated by A is a subset of D, then A divides P. Since P is irreducible, either A must be a unit or A and P are associates. Therefore, either D is equal to the principal ideal generated by A, or the principal ideal generated by P is equal to the principal ideal generated by A. Thus, the integral to the principal ideal generated by P is a maximal ideal. Corollary 18.13. Let D be equal to a principal ideal domain. If P is irreducible, then P is prime. So proof. Let P be irreducible, and suppose that P divides AB. Then the principal ideal generated by AB is a subset of the principal ideal generated by P. By corollary 16.40, since, this is just basic ring stuff. Since the principal ideal generated by P is a maximal ideal, the principal ideal generated by P must also be a prime ideal. Thus, either A is in the principal ideal generated by P, or B is in the principal ideal generated by P. Hence, either P divides A, or P divides B. Now, Oh gosh, why did I do this? Lemma 18.14. Let D be a PID, and let I1, I2, on and on, be a set of ideals such that I1 is a subset of I2 is a subset of blah blah blah. Then there exists an integer n, such that In is equal to I capital N for all n greater than n. What this shows us, basically, is that a PID, oh yeah, it satisfies the ascending chain conditions, it's a no Arthian ring. God, I'm not going to be able to pronounce that. Which is basically that whenever we have a finite tower of things, we are able to climb to the top. And once we're at the top, we can look down. That's basically what this is saying. Because in other things, if we don't have a PID, it's very possible we just have an endlessly increasing chain of things. And we can't do any finite analysis or limiting analysis. But this allows us to actually do that type of analysis. So, anyways, proof. We claim that I is equal to the union of I equals 1 to infinity. I is an ideal of D. Certainly, I is not empty, since I sub 1 is a subset of I and 0 is an I. If A and B are an I, then A is an II and B is an IJ for some I and J and N. Without loss of generality, we can assume that I is a sum I is less than or equal to J. Hence, A and B are both an I sub J, and so A minus B is also an I sub J. Now, let R be an... What in the... Oh, that was not loading in. Let R be in D and A and I. Again, we note that A is an I sub I for some positive integer t. Since I sub I is an ideal, RA is an I to the sub I, and hence must be an I. Therefore, we have shown that I is an ideal in D. Since D is a principal ideal domain, there exists an element A bar in D that generates I. Since A bar is an I sub n for some n in n, we know that I sub n is equal to I is equal to the principal ideal generated by A bar. Consequently, In is equal to I capital N for n greater than or equal to n. That is a very pretty proof. I really like that, actually. Any commutative ring satisfies the conditions in lemma 1814. Any commutative ring such that this tower of ideals eventually is constant for all ideals is said to satisfy the ascending chain condition, or ACC. Such rings are called Noether rings, after Emmy Noether. Theorem 18.15. Every PID is a UFD. So first, proof of the existence of the factorization. Let D be a PID and A be a non-zero element in D, that is not a unit. If A is irreducible, then we are done. If not, then there exists a unique factorization, no, not unique. If not, then there exists a factorization A equals A1 B1, where neither A1 nor B1 are a unit. Hence, the principal ideal generated by A is a subset of the principal ideal generated by A1. By lemma 18.11, we know that the principal ideal generated by A is not equal to the principal ideal generated by A1. Otherwise, A and A1 would be associates and B1 would be a unit, which would contradict our assumption. Now, suppose that A1 is equal to A2 B2, where neither A2 nor B2 are a unit. By the same argument as before, we get the principal ideal generated by A1 is a subset of A2. We can continue with this construction to obtain an ascending chain of ideals. The principal ideal generated by A, then A1, then A2, on and on. By lemma 18.14, there exists a positive integer n, such that the principal ideal generated by An is equal to the principal ideal generated by A capital N for all n greater than or equal to capital N. Consequently, A sub capital N must be irreducible. We have now shown that A is the product of two elements, one of which is irreducible. Now, suppose that A is equal to C1 P1, where P1 is irreducible. If C1 is not a unit, we can repeat the preceding argument to conclude that the principal ideal generated by A is a subset of the principal ideal generated by C1. Either C1 is irreducible, or C1 is equal to C2 P2, where P2 is irreducible and C2 is not a unit. Continuing to this manner, we obtain yet another chain of ascending ideals, and the chain must satisfy the ascending chain condition. Therefore, A is equal to P1, P2 all the way to PR, where irreducible elements P1 all the way to PR. Uniqueness of the factorization. To show uniqueness, let can you not do that? Let A equals P1, P2 all the way to PR is equal to Q1, Q2 all the way to QS, where each Pi and each Qi are irreducible. Without loss of generality, we can assume that R is less than S. Since P1 divides P1, Q2 all the way to QS, by corollary 18.13, it must divide some Qi. By rearranging the Qi's, we can assume that P1 divides Q1. Hence, Q1 is equal to U1 P1 for some unit U1 in D. Therefore, A is equal to P1, P2 all the way to PR is equal to U1, P1, P2 all the way to QS. Or P1, Q1 all the way to QS. Or P2 all the way to PR is equal to U1, Q2 all the way to QS. Continuing in this manner, we can arrange the QI such that P2 is equal to Q2, P3 is equal to Q3, all the way up to PR is equal to QR, to obtain U1, U2 all the way to UR, QR plus 1 all the way to QS is equal to 1. In this case, QR plus 1 all the way to QS is a unit, which contradicts the fact that QR plus 1 all the way to QS are irreducibles. Therefore, R is equal to S, and the factorization of A is unique. And as a final very nice corollary, let F be a field, then f of x is a UFD. Oh man, that's really satisfying. It's really satisfying. Okay. Example 18.17. Every PID is a UFD, but it is not the case that every UFD is a PID. In corollary 18.31, we will prove that z of x is a UFD. However, z of x is not a PID. Let I be equal to 5 fx plus xgx, fxgx, and z of x. We can easily show that I is an ideal of z of x, and suppose that I is equal to p of x, the ideal generated by it. Since phi is an I, 5 is equal to f of x, p of x. In this case, p of x is equal to p, it must be a constant. Since x is an I, x is equal to pg of x. Consequently, p is equal to plus minus 1. However, it follows from this fact that the entire principal ideal is equal to z of x, but this would mean that 3 is an I. Therefore, we can write 3 is equal to 5f of x plus xg of x, for f of x and g of x is equal to z of x. Examining the constant term of this polynomial, we see that 3 is equal to 5f of x, which is impossible. Oh, that's nice. Okay, Euclidean domains. We've repeatedly used the division algorithm when proving results about either z or f of x, where f is a field. We shall now ask when a division algorithm is available for an integral domain. Let D be an integral domain, such that there is a function nu from d over 0 to n, satisfying the following conditions. 1. If a and b are non-zero elements in D, the nu of a is less than or equal to nu of ab. And 2. Let a be in D, and suppose that b is not equal to 0. Then there exist elements q, r, and d, such that a is equal to bq plus r, and either r is equal to 0 or nu of r is less than nu of b. Then D is called a Euclidean domain, and nu is called the Euclidean valuation. So what this basically is, the Euclidean valuation gives us a sense of the, dimension or the absolute value of, an element. So, for example, nu of a times b, or nu of f of x, okay, in the case of this, we have nu of f of x equals the degree of f of x. Example 18.18. Absolute value on z is a Euclidean valuation. Then, example 18.19, oh funny, let f be a field, then the degree of the polynomial in fx is a Euclidean valuation. Example 18.20. Recall that the Gaussian integers in example 16.12 of chapter 16 are defined by z adjoint I is equal to a plus bi for a and b and z. We usually measure the size of a complex number a plus bi by its absolute value. A plus bi is equal to the square root of a squared plus b squared. However, square root of a squared plus b squared may not be an integer. For our evaluation, we will let nu of a plus bi be equal to a squared plus b squared to ensure that we have an integer. We claim that nu of a plus bi equals a squared plus b squared is a Euclidean valuation on zi. Let zw be in zi. The nu of zw is equal to the absolute value of zw squared is equal to the absolute value of z squared is absolute value of w squared equals nu of z nu of w. Since nu of z is greater than or equal to 1 for every non-zero z in zi, nu of z is less than or equal to nu of z nu of w. Next, we must show that for any z is equal to a plus bi, and w is equal to c plus di in z adjoint I, with w not equal to 0, there exist elements q and r in z adjoint I, such that z is equal to qw plus r, and with either r is equal to 0, or nu of r is less than nu of w. One can view z and w as elements in q adjoint I, which is equal to p plus qi, p and q, the field of fractions of z adjoint I. Observe that zw to the minus 1 equals a plus bi, c minus di over c squared plus d squared, and then we can basically just manipulate a bunch of stuff here. to ultimately end up with these terms m1 plus m2i plus s plus ti in q of I. In the last steps, we are writing the real and imaginary parts as an integer plus a proper fraction. That is, we take the closest integer mi such that the fractional part satisfies ni over a squared plus b squared is less than or equal to 1/2. For example, we write, oh I hate this, 9/8 is equal to 1 plus 1/8, and 15/8 is equal to 2 minus 1/8. Thus, s and t are the fractional parts of z omega negative 1 is equal to m1 plus m2i plus s plus s plus ti. We also know that s squared plus t squared is less than or equal to 1/4 plus 1/4 is equal to 1/2. Multiplying by w, we have z is equal to z w to the negative 1 w is equal to w m1 plus m2i plus w s plus ti is equal to qw plus r, where q is equal to m1 plus m2i and r is equal to w s plus ti. Since z and qw are in z adjoint I, r must be z adjoint I. Finally, we need to show that either r is equal to 0 or nu of r is less than nu of w. However, nu of r is equal to nu of w, nu of s plus ti is less than or equal to 1/2 nu of w is less than nu of w. Okay. Now, every Euclidean domain is a principal ideal domain. Proof. Let D be a Euclidean domain and nu be a Euclidean valuation on D. Suppose I is a non-trivial ideal in D and choose a non-zero element b in I such that nu of b is minimal for all a in I. Since D is a Euclidean domain, there exist elements q and r in D such that a is equal to bq plus r and either r is equal to 0 or nu of r is less than nu of b. But r is equal to a minus bq is an I since I is an ideal. Therefore, r is equal to 0 by the minimality of b. It follows that a is equal to bq and I is equal to the principal ideal generated by b. And as such, every Euclidean domain is a unique factorization domain. Okay. So factorization in D adjoint x. One of the most important polynomial rings is z adjoint x. One of the first questions that come to mind about zx is to ask whether or not it is a UFD. We will prove a more general statement here. Our first task is to obtain a more general version of Gauss's lemma. So let D be a unique factorization domain, and suppose that p of x is equal to an xn plus all the way on to plus a1x plus a naught in D of x. Then the content of p of x is the greatest common divisor of a0 all the way to an. We say that p of x is primitive if the greatest common divisor of a0 all the way to an is equal to 1. Example 18.23. In z of x, the polynomial p of x is equal to 5x4 minus 3x cubed plus x minus 4 is a primitive polynomial since the greatest common divisor of the coefficients is 1. However, the polynomial q of x is equal to 4x squared minus 6x plus 8 is not primitive since the content of q of x is 2. Now, theorem 18.24, proper Gauss's lemma. Let D be a UFD and let f of x and g of x be primitive polynomials in D of x. Then f of x, g of x is primitive. So proof. Let f of x is equal to the sum from I equals 0 to m, a sub I x di, and g of x is equal to the sum from I equals 0 to n, b sub I x di. Suppose that p is a prime dividing the coefficients of f of x, g of x. Let r be the smallest integer such that p does not divide a sub r, and s be the smallest integer such that p does not divide b sub s. The coefficients of x to the r plus s and f of x, g of x is c of r plus s equals a naught b of r plus s plus a1 b of r plus s minus 1, on and on to plus a of r plus s b naught. Since p divides a naught all the way to ar minus 1, and b naught is all the way to bs minus 1, p divides every term of c of r plus s except for the term arbs. However, since p divides c of r plus s, either p divides ar or p divides bs, but this is impossible. Spicy, I love it. Alright, lemma 18.25. Let D be a UFD, and let p of x and q of x be in D of x. And the content of p of x, q of x is equal to the product of the contents of p of x and q of x. Proof. Let p of x be equal to cp1 of x, and q of x is equal to dq1 of x, where c and d are the contents of p of x and q of x respectively. Then p1 of x and q1 of x are primitive. We can now write p of x, q of x is equal to cd p1 of x, q1 of x, and since p1 of x, q1 of x is primitive, the content of p of x, q of x must be cd. Now, Lemma 18.26. Let D be a U of D and F its field of fractions. Suppose that P of x is equal to D of x, and P of x is equal to F of x, G of x, where F of x and G of x are in F of x, or F adjoint x. Then P of x is equal to F1x, G1 of x, where F1 and G1x are in D of x. Furthermore, degree of F of x is equal to the degree of F1 of x, and degree of G of x is equal to degree of G2 of x, or G1 of x. Proof. Let A and B be non-zero elements of D, such that A f of x, B g of x are in D of x. We can find A1, B1, and D, such that A f of x is equal to A1 f1 of x, and B g of x is equal to B1 g1 of x, where f1 of x and g1 of x are primitive polynomials in D of x. Therefore, ABP of x is equal to A1 f1x times B1 g1 of x. Since f1 of x and g1 of x are primitive polynomials, it must be the case that AB divides A1 B1 by Gauss's lemma. Thus, there exists a C in D such that P of x is equal to C f1 of x g1 of x. Clearly, degree of f of x is equal to degree f1 of x, and degree of g of x equals degree of g1 of x. Alright, the following corollaries are just direct consequences of lemma 18.26. Corollary 18.27. Let D be a U of D and F its field of fractions. A primitive polynomial P of x in D of x is irreducible to F of x if and only if it is irreducible in D of x. Corollary 18.28. Let D be a U of D and F its field of fractions. If P of x is a monic polynomial in D of x, with P of x equal to F of x, G of x, and F of x, then P of x is equal to F1 of x, G1 of x, where F1 of x and G1 of x are in D of x. Furthermore, degree of F of x is equal to degree of F1 of x, and degree of G of x is equal to degree of G1 of x. Now, theorem 18.29. If D is a U of D, then D of x is a U of D. Here we go. Proof. Let P of x be a non-zero polynomial and D of x. If P of x is equal is a constant polynomial, then it must have a unique factorization since D is a U of D. Now, suppose that P of x is a polynomial of positive degree in D of x. Let F be its field of fractions of D, and let P of x be equal to F1x, F2 of x, all the way to Fn of x, be a factorization of P of x, where each Fi is irreducible. Choose A sub I and D, such that A sub I, Fix, is in D of x. Then, there exists B1 all the way to Bn in D, such that AI, Fi of x, is equal to Bi, Gi of x, where Gi of x is a primitive polynomial in D of x. By corollary 18.27, each G sub I of x is irreducible in D of x. Consequently, we can write A1 all the way to An P of x equals B1 all the way to Bn of Gx, all the way multiplied by itself up to Gn of x. Let B equals B1 all the way multiplied to Bn. Since G1x times Gn all the way to Gnx is primitive, A1 to An divides B. Therefore, P of x is equal to A G1 of x all the way to Gn of x, where A is in D. Since D is a U of D, we can factor A as WC1 all the way to CK, or no, UC1 all the way to CK, where use the unit and each of the CI's are irreducible in D. We will now show the uniqueness of this factorization. Let P of x be equal to A1 all the way to AM, F1 xn all the way to Fnx, is equal to B1 all the way to BR, G1 of x all the way to Gn of x. Be two factorizations of P of x, where all the factors are irreducible in D of x. By corollary 18.27, each of the F sub i's and G sub i's are irreducible in Fx. The AI's and BI's are units in F. Since F of x is a PID, it is a U of D. Therefore, N is equal to S. Now, rearrange the G sub i's x so that F sub I and G sub ix are associates for I equals 1 to N. Then, there exists C1 all the way to Cn and D1 all the way to Dn and D, such that Ci over Di, Fi, x is equal to Gix, or Cifx is equal to Gi of x. The polynomials Fi of x and Gi of x are primitive. Hence, Ci and Di are associates in D. Thus, A1 all the way to Am is equal to WB1 to BR in D, where U is a unit in D. Since D is a unique factorization domain, M is equal to S. Finally, we can reorder the BI's so that AI and BI are associates for each I. This completes the uniqueness part of the proof. Oh my god. That's a lot. That's a lot. Oh my gosh. I'm gonna definitely be like rereading this on my own in the personal time because there's so much going on in these proofs with factorization. Oh my gosh, okay. Corollary, 18.30. Let f be a field. Then f of x is a UFD. Corollary 18.31. The ring of polynomials over the integers, zx, is a UFD. Corollary 18.32. Let d be a UFD. Then d of x1 all the way to xn is a UFD. Remark 18.33. It is important to notice that every Euclidean domain is a PID, and every PID is a UFD. However, as demonstrated by our examples, the converse of each of these statements fails. There are principal ideal domains that are not Euclidean domains, and there are unique factorization domains that are not principal ideal domains. Think of Z adjoined X. Sage nay. Historical note. Carl Friedrich Gauss, born in Brunswick, Germany on April 30th, 1777, is considered to be one of the greatest mathematicians who ever lived. Gauss was truly a child prodigy. At the age of 3, he was able to detect errors in the books of his father's business. Gauss entered college at the age of 15. Before the age of 20, Gauss was able to construct a regular 17-sided polygon with a ruler and compass. This was the first new construction of a regular n-sided polygon since the time of the ancient Greeks. Gauss succeeded in showing that if n is equal to 2 to the 2 to the n plus 1 is prime, then it was possible to construct a regular n-sided polygon. Gauss obtained his PhD in 1799 under the direction of Pfaff. Oh god, I don't know. I'm not gonna know how you pronounce that. At the University of Helmstedt. In his dissertation, he gave the first complete proof of the fundamental theorem of algebra, which states that every polynomial with real coefficients can be factored into linear factors over the complex numbers. The acceptance of complex numbers was brought about by Gauss, who was the first person to prove to use the notation I for square root of negative 1. Gauss then turned his attention towards number theory. In 1801, he published his famous book on number theory. It's Inquisitions into Arithmetic, something similar to that from the looks of it. I'm not even going to try to properly pronounce that. Throughout his life, Gauss was intrigued with this branch of mathematics. He once wrote, mathematics is the queen of the sciences, and the theory of numbers is the queen of mathematics. In 1807, Gauss was appointed director at the observatory at the University of Göttingen, a position he held until his death. I can't read. This position required him to study applications of mathematics to the sciences. He succeeded in making contributions to fields such as astronomy, mechanics, optics, geodesy, and magnetism. Along with Wilhelm Weber, he co-invented the first practical electric telegraph some years before a better version was invented by Samuel F.B. Morse. Gauss was clearly the most prominent mathematician in the world in the early 19th century. His status naturally made his discoveries subject to intense scrutiny. Gauss's cold and distant personality many times led him to ignore the work of his contemporaries, making him many enemies. He did not enjoy teaching very much, and young mathematicians who sought him out for encouragement were often rebuffed. Nevertheless, he had many outstanding students, including Einstein, Riemann, Kummer, Dirichlet, and Dedekind. Gauss also offered a great deal of encouragement to Sophie Germain, who overcame the many obstacles facing women in her day to become a very prominent mathematician. Gauss died at the age of 78, in Göttingen on February 23rd, 1855. So, reading questions. Okay. Integral domains are the abstractions of which two fundamental rings that we have studied already. They are the abstractions of, get this out of the board, Z and, dare I say, Z adjoined X. What are the various types of integral domains defined in this section? We have UFDs, PIDs, and Euclidean domains, those being the main ones. The field of fractions of ring abstraction abstracts from what ideas in basic mathematics, the rational numbers. In the previous chapter, we had a theorem about irreducible polynomials generating maximal ideals, which theorem in this chapter generalizes the previous result. About irreducible polynomials generating maximal ideals. The valuation maps. Actually, yeah, the valuation maps. Describe an example which is a UFD but not a PID. Good. You can just take Z adjoined X. Or many multiple variable polynomial rings. So I will not belabor that point. Oh man, and now the exercises before I do the intermission time. Alright, I'm back, and I've got some coffee, so I think we're ready to begin. Alright, so I'm not feeling computation push. I don't know if you were there for any of the earlier streams if you're watching this. I like how I speak like I'm talking to a specific person. But I'm not really interested in these computation things. Like, if this is true, show that Z must be a unit. And Gaussian integers or UFDs, so factor each of those into like irreducibles. It's not really my style. Like, the most I can do is like, for example, something that's really interesting to note is if I remember, it's 2 plus I. Yeah, 2 plus I, 2 minus I is our actual factorization of the number 5. And then each of those have like the obvious irreducible stuff. Anyways. Let D be an integral domain. Prove that FD is an abelian group whose abelian group is a group. Oh, brain. Oh my god. Okay. Prove that FD is an abelian group under the operation of addition. Okay. So for this, we define AB. Yeah, I don't write it out in that way. AB plus CD is equal to AD plus BC over BD is equal to CB. I think you just read, you just read it, DA plus CB, because this comes from the commutativity of our ring. So DA plus CB over BD is equal to D, or yeah, it's equal to C over D plus B over A. You would probably just flip these around, but because it's a commutative ring, and then we have an abelian group as well, that would work. So you have that, so that shows that it's abelian. I show the operation multiplication is well defined in the field of fractions. Also, let me make sure I'm actually... Okay, I can hear myself again. I don't know why my Twitch stream is like a stupid amount of seconds delayed. So, show that the operation of multiplication is well defined in the field of fractions, FD. So what you want to show is that if A, B is equal to A prime, B prime, and we have that C, D is equal to C prime, D prime, we need to show that A, B, C, D is equal to A prime, B prime, C prime, D prime. So let's compute this. So canceling that out for now, we get A, B, C, D is equal to AC, BD. Alright, and we want to show that this is equal to A prime, C prime, B prime, D prime. So what we want to show is that instead of scrolling down, let me just like move all this up, like shoop. Oh no, that's far too short, okay. No. Alright, and what we want to show is that AC, B prime, D prime is equal to A prime, C prime, BD. So for this, we just use the commutativity to factor it into AB prime, CD prime is equal to A prime, B, C prime, D. And using the definitions of equality up here, for this, it's obvious that this is equal to, I'll just do this. This is equal to A prime, B, C prime, D. So this equality holds. which shows that these two elements are equal, which means that multiplication is well defined on the structure. Okay. Oh my gosh, let me reload Twitch, because Twitch is really bad in terms of delay right now. Verify the associativity and community I'm gonna hope that you have seen enough of it to know why the associativity and commutativity works. It's just kind of a pain to actually completely write out, so I'm not gonna worry about that. Excuse me. Proof. Proof or disprove. Any subring of a field F containing 1 is an integral domain. Huh. That's actually kind of interesting. So any subring of a field F containing 1 is an integral domain. Suppose we have an integral domain D, and suppose that we have a subset, just a subset of D, call it A. Then from here, what we have is, suppose now that AB in A is equal to 0. Well, that would imply that AB is equal to 0 in the commutative ring, in the integral domain as well. So that would imply that AB is actually, like, AB is equal to 0 for A and B not equal to 0. That would imply that in the, like, actual integral domain we're working over, we have that identity as well. So it cannot be the case. So, I'm just wondering, something which feels weird about it. Because, like, this feels obviously right, because a subring of a field F is a subring of an integral domain, and you don't even need the field, you just need the integral domain part. Yeah, I mean, another way we can say that is the restatement that a field is an integral domain. I'm kind of confused about what this problem specifically wants, and I'm hoping that I'm not missing anything. I'll just leave it at that for now, yeah. Proof or disprove, D is an integral domain, then every prime element in D is also irreducible in D. So this is, I imagine this is going to be false. How do I show this? So we need that every prime element in D is also irreducible. So if P divides AB, then P divides A, or P divides B. So we have that, and we need to show from there that if P is equal to CB, then, or actually, this is a good thing. If P is equal to AB, then either A or B is a unit. So let's think about this. During a situation like this, what I tend to do is that I try to find what conditions look up. So P is equal to AB. This means by definition that P divides AB, considering we're assuming our ring to have identity. So either P divides A or P divides B. So then we have that A is equal to PC, which means that P is equal to PCB, or that 1 is equal to CB, which means that C and B are units, which means that B is a unit. So let me double check that I didn't do my math wrong here, but it looks like the case that every prime element in an integral domain is irreducible. And we need that integral domain part because, yeah, let me go, every prime in an integral domain Oh my god, why do I keep randomly muting? I'm just gonna keep doing this. Anyways, I was saying that this is... Oh gosh, do I not even... Oh, I didn't even have sound for what I was writing on the board. Basically, I was writing that if it's of characteristic 0, you take the thing made up by integer multiples of 1, or integer multiples of the action of the integers on the element 1. That gives you a, like, subring isomorphic to the integers. And then from there, it's your field of fractions can be properly embedded by the previous theorem, or by one of the previous theorems. And that gives us, because of just like the canonical identifications, gives us a subfield. It gives us a subfield isomorphic to the rationals. All right. Oh my gosh, I did this before. At least I caught it earlier this time. Let f be a field, and then I said for this, it's just basically the switching of the brackets for the fractions in both of these. Let p be prime, and denote the field of fractions of zpx by zp of x. Prove that zp of x is an infinite field of characteristic p. Ooh. Okay. Shh. So first of all, it's obvious that this is... Oh, it's actually, this is way easier than I thought it was going to be. Or maybe I shouldn't speak too soon. Actually, maybe I do speak too soon. Maybe I don't. So, zp of x. So first of all, it's an infinite field because zp of x is like already infinite, and taking its identification into zpx, the under the obvious canonical identification, gives us another infinite field. Why is Twitch so slow? I just heard myself talk about randomly muting. Prove that zp of x is an infinite field of characteristic p. So basically what I want to show is that, let's suppose we have f over q of x. I'll just denote them by f over q. So we have f over q plus f over q is equal to... So we'll do induction. So f over q plus f over q is equal to f q plus qf over q squared is equal to f of... is equal to 2 times f of q, 2 times f q over q is equal to q squared is equal to 2 times f over q. And since the characteristic of any, like, the characteristic of the main element is p, because we're working z mod p, then the characteristic of anything else under this identification will then be p. Nice. Easy. Okay. Prove that the field of fractions of Gaussian integers is the rational of Gaussian stuff. I'm lazy. Okay. A field f is called a prime field if it has no proper subfields. Oh, this is actually a really cool thing. If E is a subfield of f and E is a prime field, then E is a prime subfield of f. So prove that every field contains a unique prime subfield. But I'm wondering, yes, okay. So suppose we do the same so we'll construct our prime subfield this way. First, we take our element 1 in f. Then we make this set z acting on 1, which is defined to be the set of all m times 1, such that m is in z. Let's quickly show that this is an integral domain. So it's a group because it's, or you can say it's more formally a group action. Plus n times 1 equals m plus n times 1. So that shows that we have an abelian group structure, because also this is abelian. Because it's a cyclic group generated by 1. And to show it's a ring structure, we simply define m m.1 n.1 to be equal to mn.1. And all the rules naturally follow from there, so we get a ring structure. And as well, it's an integral domain structure. Yes, it's an integral domain structure because this is because F is a field and has such an integral domain. Okay, so from there, yeah, we have this. So now we form, we'll call this S for now. So now we form F of S. Note as well that we have this. S has an embedding into our field F. Oh, let me also fix that one. And also has an embedding into F of S. Because this is the same diagram we drew before, we know there's a unique, note the uniqueness here, isomorphism into that. And it will be the smallest subfield containing 1. And because it will be the smallest subfield, actually, we should probably prove that. So, actually, I won't properly completely prove it. I'll just give an intuitive argument because, like, all the rest of the stuff would basically be like putting the argument in the context of well orderings. So suppose that we have any other subfield. First of all, it's going to contain all of these, just like as a subgroup. That contains the identity. And then from there, naturally it has to contain all the inverses of all that, which is functionally what the field of fractions does. And from there, you've already reached S. All you can do is like exceed it. So this uniquely determines our prime subfield. And oh, that uniqueness is really cool. The fact that it uniquely determines it. Oh my gosh. Okay. So from here. Alright, if use the subfield and of F and E is a prime field. Yeah, we have a unique prime subfield. So the prime subfield is isomorphic to Q, because if it's of characteristic 0, that we basically have what this is, what that S is. S is isomorphic to Z if characteristic of F is equal to 0. And S is isomorphic to Z mod P if characteristic of F is equal to P. And then from there, yeah, the rational numbers. So, okay. And actually, that's... So what we want to do, something that's actually really interesting. So prove that, okay. What we want to prove is that phi, we have an isomorphism from the integers mod p to f, the integers mod p. So basically, the group, this group, is isomorphic to its field of fractions. Alright, how do I do this? So we're going to assign, obviously all we can really do is assign phi of n to be equal to the equivalence class n1. So it should be obvious that, in this case, it should be obvious that this is injective. It's an embedding into that image. Now to prove that it's surjective, so suppose we have A, B. If we have A, B, then we have is equal to A1 times 1B is equal to A. Wait, something I'm wondering. a1 times b to the negative 1, which is equal to phi of ab minus 1. So this shows, okay, this shows that if this map is injective, that a field is actually isomorphic to its field of fractions. Now, what I'm wondering is, when is the map injective? So suppose that phi of n is equal to phi of m. Then n1 is equal to m1, which implies that n is equal to m. Oh, so it's always injective in a field, it looks like. Right? Wait, let me double check this. So it definitely is going to be the case for the integers mod p, because z mod p is already a field. I just want to check that this is actually, like, a canonical identification, and I'm not making a very silly mistake. So what, a field is isomorphic to its field of fractions. Something about that sounds wrong. Alright. Oh, wait, no, stack exchanges are currently down for maintenance. Oof. Oh gosh, I can't find it. Alright, oh, I can't find it. It looks true. It looks like it holds. Yeah. I can't argue with the facts. It looks like the field of fractions is indeed isomorphic to the field, if it's a field over which we're working with in the first place. Which is weird. Anyways, okay, I'm gonna stop being confused. Shh. Alright, now, let z mod 2, nah, I'm lazy. And not computation, me hate numbers. So let, db of d, an element d and d is the greatest common divisor of a and b and d. If a d divides a and b divides b, and d is just by any other element dividing both a and b. There's this unique common. Up to its shits. That is, if d and d prime are both greatest common divisors. So for this, okay. Let you, okay, for this, because we have a unique factorization domain, equals p1, p2 all the way to pm, and b be equal to q1, q2 all the way to q of s. Now, let define GCD of A, B to be equal to the product of all PI, the product of all PI, such that PI equals UI equals U QJ, or QJ for some unit U. Some unit U. PI is found to be the PI equals UQJ for some unit V, some unit U. Then from there we can just use unique factorization and associates to like easily show that this is the greatest common divisor. I'm going to leave the exercise of that to the viewer because I'm lazy. If B is a PID and A and B are non-zero elements for the existing elements S and T, such that the greatest common divisor of A and B is equal to AS plus BT. I think it's going to be something where I can I can't, my brain is failing me right now. Alright. So we have the intersection of those two. I'm not gonna worry about it. My brain is just like failing me at the moment. Let D be integral domain. Oh yeah, okay, it's 12b. I'm gonna do that on my own time. I'm not gonna make the same mistake of saying I'm gonna do this next time on stream and spend 10 minutes at the beginning of stream unnecessarily. But I will do this later in my time. Let D be an integral domain. Define a relation A and isomorphic to B if A and B are associates. This is just the fact that units have inverses basically, and units exist. Let V be Euclidean domain with the Euclidean valuation. If U is a unit in D, show that V of U is equal to V of 1. Alright, with the Euclidean valuation V. So let's quickly search up what they specifically define the evaluation to be, because I don't want to make once more a fool of myself. Alright, V is an element from D to N union 0 if A and B are non-zero elements in D, nu of A is less than or equal to nu of AB. Oh yeah. An easy way to show it is that nu of U is less than or equal to nu of U inverse is equal to nu of 1. And as well, nu of 1 is less than or equal to nu of U1 equals nu of U. So nu of U equals nu of 1. If I got that right. Yeah, looks like it. Alright, give me a second to scroll back down. Oh god, my computer, no. Okay. Yeah, okay. It was asking for equality, like full inequality. I won't delay erase that now yet. Alright, if A and B are associates in D, it's a similar argument by just using the unit inverse. Show that Z of square root of 5 joined I is not a unique, prove every subdomain of a U of T is also a U of T. That's a good question, actually. I don't think so. Because I don't think you'll necessarily have those irreducibles in just a subdomain. Alright, an ideal of a community ring R is said to be finitely generated if there exist elements A1 all the way to AN and R such that every element R in the ideal can be written as A1 R1 all the way to AN Rn for some R1 all to Rn and R. Prove that R satisfies the ascending chain condition if and only if every ideal of R is finitely generated. So obviously, is if an ideal is infinitely generated, that means it can't be generated by anything finite, which means that you have to like slowly append those ideals. So ACC implies every ideal is finitely generated. Every ideal is finitely generated implies ACC since you just choose one of those, and since each time the ideal generated by n is a subset of one of the ideals as you ascend up the tower, and then eventually you're going to hit a limit. Yeah, because it would imply then, if you didn't, that you would have an infinitely generated ideal. Okay, sick. I'm not going to write down the full details, considering this is like... Also, I do plan on eventually, possibly, maybe, no promises yet, going through a commutative algebra textbook. And this is very much a problem you would do in that. The descending chain condition. Alright, show that D satisfies the descending chain condition, it must, show that if D satisfies the descending chain condition, it must satisfy the ascending chain condition. So let D be an integral domain with a descending chain of ideals, I1, I2, all the way to I3. Suppose there exists an n such that ik is equal to in for all k's greater than or equal to n. So a ring satisfying this condition is said to satisfy the DCC. So suppose that we have a decreasing set of ideals. Okay. So for this, let I1 subset I2 subset of blah blah blah. So we let I be equal to the union of I sub j I'm trying to think of what to work here. So we want to turn this ascending chain into a descending chain. What's like a dual thing that would generalize well, taking these inclusions and making them sub-inclusions. So I1, I2, so we have ideals, we can multiply. The problem is because the subset will just be stuck at the same thing. So I'm just trying to think of an operation we can do to like restrict the domain every time. I mean, okay, let's think. One thing we can do is, because these are ideals, they're ideals of a ring R. And we know that R over I1 is, in a sense, a superset of R over I2 is a superset of on and on. Right? But how do we make this inclusion precise? Because they're not all taking place in the same universe. mean, I guess one way to say it, I guess this is less so an exercise on what it specifically is and more so on making the intuition precise. Oh gosh, Twitch is having a moment as well. Give me a second to make sure the stream is not actively horribly failing. So one way to say it is that for phi of r over I1 to r over I2, oh, I think that's how we get this structure. I think I get it. I think I'm starting to get it. So if we have a plus I, right, if a plus I1, we can send it to a plus I2. How do we know this is well defined? Well, because I1 is a subset of I2. AI1 is, like, anywhere it's properly defined to be the same, it will be sent on the identity to that thing. So we can naturally identify these with each other in the space of ideals. So let's think of what we're working. What in the world is going on with Twitch? Alright, hopefully it's... So we can also think of this as being R over the principal ideal. Which in this case is just isomorphic to R. Now, are each of these ideals... By the way, like once we, if we show that each of these are ideals, the descending chain condition obviously implies this ends at some point, which obviously implies the ascending chain condition. So R over I1 is R over I. Okay, what do we define R over I1 to be? Let's think. So R over I1 identifies I1 and R over that, and oh yeah. It identifies all elements that are sent to the kernel of R over I1, which is a set of I1. So we can then reasonably talk about the universe of this. Oh yeah, and then since we can talk about the universe, each of these are ideals, because it's isomorphic to this. Oh, okay, it's all making sense now. I guess the one thing I just want to make absolutely sure is that all these are ideals. So we define R over I1 as a subring of R over 0 to be equal to the set I plus 0 for I in ij. And now we want to show that this is a principal ideal or an ideal. So for this, we move all this up here. Oh, that's cool. Oh, that is cool. Because I was like, what's going to give us this contravariance? Alright, so first of all, this is obviously because of the subring structure on this. This is obviously a subring. Now let's show. So we have A, I plus that is equal to A, I plus that. Is in, yeah, so it's obviously an ideal, and that contravariance implies the descending chain condition implies that it stops at some point, which implies that this stops ascending at some point. Awesome. Oh my god, awesome. Okay. I guess I'll like rush after that. Oh, it's so good. That's so good. Oh, it's so good. It's so good. I'm happy. Okay. Alright, let R be... Oh, okay. We're getting into some... This is like beginning of commutative algebra right here. So I'm going to really emphasize that. So I'll let R be a commutative ring with identity. We define a multiplicative subset of R to be a subset S such that 1 is an S and AB is an S if A and B are an S. Define a relation sim on R times S by AS is similar to A prime S prime if there exists an S star in S such that S star S prime A minus S A prime is equal to 0. So okay, basically what this is so A S. Eventually we'll be writing it in this notation anyway, so I'm just gonna, oh no, erase that. So I'm just gonna write it in this way. AS is equal to A prime S prime if there exists an S star such that S star of A S prime minus A prime S is equal to 0. Which, as you notice, normally this definition already completely works if we have an integral domain, but this actually generalizes that, because it's very possible we have a commutative ring, just not with an integral domain. Alright, so show that that's an equivalence relation. Obviously, if it's the same thing, then this just evaluates to 0 regularly. This is symmetric in its arguments. It's just reversing them is fine. And a lot of it is like, suppose S star of A S prime minus BS equals 0, and S star of B of S prime, B of S prime prime minus C S prime is equal to 0. So then we simply let's think. This is the same. So we want to show that there is an S star such that A S prime prime minus CS is equal to 0. So we want to show transitivity on this relation. Let me pull the whole thing up a quick bit. So S prime prime minus CS is equal to 0. So let's think. So first of all, let's consider the fact that in this equation, using the distributive property, we have S star A S prime minus S star BS is equal to 0. As well, we have S star BS prime prime minus S star CS prime is equal to 0. So for this, because we're going to be using the fact that it's a multiplicative set, I just don't exactly know how without making the computations extremely ugly. So we'll start by noticing that the final computation will simplify to S, I don't know, triangle we'll call it because I'm lazy. A S prime prime minus S triangle CS is equal to 0. So what if we start by defining, we include in the definition S star, which would imply that, or S, what if we go wild and we basically call it S star, S star, star, S, S prime, S prime prime is equal to S delta. So what we want to show is that, oh, this is horrible looking, okay. So we want to show that defining it like this will give us an identity. So first of all, what can we convert S prime into? This is what we want to show. This is equal to S delta. So S prime, S star, S prime will get us S star, S prime, actually. So first of all, notice that we have S star, AS prime prime, or AS prime. Everything else in this, such as S star, star, S prime prime, is unnecessary. At least at the moment. And then minus, what do we have with C? So we have C S prime. So we have S star, star, C S prime. This is, I hate this, but it might just work. Also, the nice thing is that if we multiply by extra things, like as long as S delta has the minimum amount of information, all the algebraic dust will actually cancel. So minus S star star, CS prime. And then make sure I have the rest of the details down. CS prime, S, SS, SSS, S prime prime, S star, something like that. This converts to, by this identification, this converts to S star BS something here. We'll just call this something like X1 minus this conversion here gets us S star star BS prime prime X2. Oh, and then from here, like the X2, we can just pull out terms as we need. And then we'll show that these two, like, we can distribute out everything else and just keep the S star star BS stuff and show that they're equal in terms of that part of the distribution. And yeah. Oh, wait, it's a bit more subtle than that, ain't it? Oh, fuck. Okay. Let's think about this more carefully. This is like a beginning of commutative algebra, so I'm going to actually treat it with a certain amount of respect. So now we have S delta. We want S delta of A S prime prime minus S delta CS equal to 0. So what I could do is my first conversion, we have that S star, S prime divides A. So we have S delta divides S delta. So we have currently an extra amount of information X1, and then S star S prime A S prime prime minus x1 s star s prime s c, which this identification up here, actually this identification over here, gets us that this is equal to x1 s star bs s prime prime wait, now we have that. Wait, minus x1 s star s prime s c moving this up, we now assume that s star star divides s delta to get us x2 s star star s star b s s prime 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 minus x1 s star star s prime sc. And it looks like we might finally get somewhere. Oh my god, this problem is a notational nightmare. Alright. Now, with this, we can rearrange this to be s star star b s prime prime. Then we have s star s. This simplifies to s star star c s prime, which means that this entire thing, you know what, screw it, I'm bringing out the big guns, I'm bringing out the working whiteboard, which means that this thing is equal to s prime prime c s prime, all pulled out of x2 s prime s, correct, because we use that, yes, s star x s star s minus x2 fix that x star, no, s x2 s star s x2 s star s prime c. Oh wait a second. And this, if we just let x2 equals 1, which implies that s delta is equal to, what is it? My brain is failing me. We prove, so we have s prime s star star. If we have this, then we have, it implies that we actually have 0. So it implies transitivity. Oh my gosh, okay. Oh my gosh, that was a nightmare of a computation. I hated that. Anyways, moving on. Now transitivity, we've shown an equivalence relation, so we've shown all we need. A student of the equivalence class. S negative 1 R be the set of all equivalence costs with respect to sigma. Find the operations as per usual. Yeah, as per usual, respectively. Prove these operations are well defined on S1 R, and that's it's got the ring of quotients of R with respect to S. Alright, so suppose that A over S, we want to show that A over S plus B over S prime is equal to C over S underlined plus D over S prime underlined if A over S is equal to C over S underlined and B over S prime is equal to B over S prime underline. So with this, we want to basically show that AS prime plus BS over SS prime is equal to excuse me, is equal to C S prime bar plus D S bar over S prime bar. So this is the way, this is basically saying that there exists, so A S prime SS prime bar plus B S SS prime bar minus C S bar S prime minus D S bar SS prime. There exists a S delta such that that is equal to 0. Oh, computing this S delta is not going to be pretty, is it? Oh gosh, okay. Alright, man. Let me just like move that up and scrunch it up a little. Whoop. So we know there's some S1 such that S1 A S bar minus CS is equal to 0. And we know there's some S2 such that S2 B S prime bar minus D S prime is equal to 0. I'm wondering. Like, I feel like we can probably use an amalgamation argument to show that this is one possible such S. But this is kind of overkill, and I don't want to prove it manually with that. So let's see what we need. So we want these things to cancel out in nice ways. something to note is that there's an S in this and not an S in that. So first of all, if we have S and S bar, we're able to factor out everything. So basically, if S and S bar, if S and S bar divide S delta, then these two terms cancel out. Because you can factorize them in terms of the extra factors. And from there, that's going to be a similar argument, I imagine, for if S prime and S bar prime, yes, divide S delta, divides these out. So if S delta is equal to S bar, S prime, S bar prime, then this evaluates to 0. Oh, no, yeah, you do actually also need to multiply in the S1 and S2. Don't worry about that, though. Shh. Oh, wait, actually, yeah, literally showed that the overkill option was like the option that you needed to choose. Nice. Yeah, these are informationally not very efficient in terms of just like writing them down, but it works. Okay. And then like we define that similarly. Show that the map psi, which since it's 1 is a ring homomorphism. I'm just gonna leave it as should be obvious because I'm lazy. Actually, wait, let me do, this is like actually kind of subtle. So C, oh I know, yeah, it does naturally follow, never mind. It's like the exact same computation, but it's just not ensured to be 1-to-1. So if R has no 0 divisors and 0 is not an S, then psi is 1-to-1, which is basically just the fact that like, if it has no 0 divisors, then it's an integral domain. And as such, S prime, since it doesn't equal 0, the original computation in here must be 0, not this. So we basically just have a field of fractions situation going on, except a possibly more expanded scope of the field of fractions. P is prime only if S is prime is 2. If and only if Rs equals R over P is a multiplicative subset of R. Yeah. Okay. If P is a prime ideal of R and S is equal to R over P, show that the ring of quotients has a unique maximal ideal. Any ring. Ooh. That is okay. That's actually very nice. Local rings are very intensely studied in the subject of commutative algebra. Like local rings are your bread and butter. They're kind of like they're as ubiquitous as groups and rings in this. Oh man, actually, just because I've just kind of getting my blood pumping for commutative algebra, I'm just going to leave this as is for now. I'm going to leave this problem quietly lay, and I'm gonna go pick up my old book from Hideaki Matsumura. Oh my gosh, but that was good stuff. That was good stuff. And especially since I need to start doing this more often. I don't like to skip things, but like, no. So many of the computation things, there are some essential computations, but a lot of these computations are just for like refurbishing your understanding, and it's late, and I don't want to waste the time. Because like this, like I mentioned, this is ultimately a review for me, so. Also, I always keep forgetting that Zariski wrote a commutative algebra book. That's my bad, though. Anyways, oh man. This is potentially going to be this next chapter. Let's take a quick look through it. This next chapter is either going to be extremely painful or not. It looks like it's going to be somewhat painful. But actually, I might even do this later tonight, because especially this brings us to vector spaces, which is way more. Not doing vector spaces tonight, but kind of doing this to get that out of the way and ready. and also considering how kind of chill a lot of Boolean algebra stuff is. I might do this later tonight, yeah. I might figure out how to put some like lo-fi music in the background or something like that. Just kidding, no, it's a horrible idea considering I'm intending this to be an almost audiobook. Shh. But anyways, yeah, I guess I'll do my normal outro. Thanks for tuning in. Have a nice day.